All right, you all. Hope everybody's doing okay. Sorry for being doubly late, actually. Believe it or not, I actually gave the whole stream just now, but I didn't realize, I don't know what I did with the software. It actually didn't stream. So it looked like it was streaming on my end, but then when I went to look at the video, it wasn't streaming. So I don't know what happened. So I'm gonna bring up my poster board again, and now pull through. At least I was able to correct some typos. A few typos in that are in there that I corrected. But I'll go ahead and go through the presentation again, and maybe somebody's still on or up. Maybe y'all want to come and check it out. Let's see here. There we go. So this is what I prepared to talk about today. I had basically as a poster presentation that I'll be doing for one of my astronomy classes, my astronomy research class. Some of you know that I have an interest in stellar rotation, and actually I adjusted the size of this window for the paper. Let me adjust the size back. Go. So that's better. So I have my some interest in stellar astronomy and in stellar rotation. So you know that I measured the rotation of the sun recently, and but for my project, my mentor has let me know I need to have something with a little more, need to go a little bit deeper, more specific, more focused into a topic. So I thought to look into the rotation of stars and clusters of stars. So if you look at this poster here, this is basically what I'm reading on now as I try to find out some niche in that data that I'll focus on trying to find. So, unsurprisingly enough, the idea of cataloging a cluster of stars and sort of plotting the distribution of rotation has already been done. So, I'll be looking into seeing what different way of analysis I might be able to do with this data here. So what I'll do is go ahead and read through the different sections. Or perhaps I'll pull up the paper as well and scroll through that. And now that I'm certain that the thing is actually streaming this time, so those of you who you all went to sleep or whatever, hopefully y'all can take a look tomorrow. Put some comments in the comment section on the video, and I plan on being at my regular time on next week at 8, and maybe I'll go in more detail about this or that as far as the rotation and what I'm finding out as I finalize the project, at least the report for the first part of the project. So to read the paper title, 3K2 campaigns yield rotation periods for 1,013 stars in Praesepe. So Praesepe is a cluster of stars that it seems is very popular for scientists to study and get the masses and declinations and right ascensions and colors and temperatures and masses of these stars. They accrued an enormous amount of data on these stars from the spectra they've been reading from them in over several days. And a poster by Darrell Berry Jr. on a eponymous paper by Dr. Raina Rapelli et al. And I actually learned about her when she actually came and spoke at UT a few weeks ago. It would have been nice to catch that talk. I think I was like studying at the time for an exam or something, and at the time that the talk was going on, and but I made a note of the speaker and went and found the paper, and it's actually, in my novice understanding, at least a very good paper. And but I think in general, people would think it's a good paper as well, like even established astronomers. And so to read what it says on the next line. It says Praesepe is a 670 mega-year-old star cluster, of which Dr. Rampelli and her team, henceforth referred to as Rampelli, took a census of rotation periods, which I'll call PROT, of 1,013 less than or equal to 1.3 solar mass stars. They compared rotation measurements across 3 surveys over 3 years and discovered that rotation period measurements are viable even if measured only once. And I'll probably update that conclusion section right there and talk about the fact that they did, for instance, this at the time in 2021, if I remember right, this was written. They made the most up-to-date and complete sample of rotators in Praesepe. And I've been noticing they've been saying rotators. I thought all stars rotated, so I wonder if there's some stars that don't. Rotators. And from K2 light curves and Gaia astrometry. And other things they're doing, they increased the number of rotators with the expanded viewing from Gaia. Another thing they did was confirm the consistency of measurements. Satellites are still relatively new as far as the practice of astronomy goes. Back in the day, they did, by sight, like I spoke about in another video. And then they came with the telescope, and still they were pretty basic telescopes by our standards. Now we have satellites in space that can look at these things. So, but what they found is when they compare, for instance, the rotation speeds that were reported from, believe it or not, ground-based telescopes, these good ground-based telescopes that can still get enough detail from these things to get rotation periods, and I'll talk about how in a little bit. But it was able to confirm the accuracy of that data to within 10%, which is very good in astronomical standards. We're looking at things so far away. So they were able to determine, well, I'll put that there, that not only over different surveys, but over the same survey over 3 years, the same satellite over 3 years in different campaigns, able to confirm that the measurements that they're making are consistent and confirming the veracity of the measurements. So looking at the one on the top left box, it says a color magnitude diagram showing differences between the legacy and updated catalogs. Rampelli accrued 220 new measurements and confirmed 793 previous measurements. So if you look at the legend, it says legacy catalog for the dots that have an outline on them, and the new members are the circles with the outline on them. So they added many new stars. And if you remember my previous videos about mentioning the HR diagram, you can see that this is reminiscent of an HR diagram. So if you look at the top line is showing the categories of stars. So generally, if you look at an HR diagram, it starts from O on the far left, then B, and then we get to A. But again, this one is of low mass stars, 1.3 solar masses or less. Therefore, we can see why it'll eliminate the O stars and the B type stars, because looking at the HR diagram, the upper left is the more massive stars. So the upper left on the HR diagram is more massive. Those would be the O stars, the B stars, and the lower right will be the lower mass stars, like the M stars. So stands to reason why we won't have any O or B stars in this survey, since we're looking at smaller stars. I'm looking at the x-axis on this thing. That's the magnitude of the stars. And interesting thing is the magnitude is actually in reverse in astronomy. So the lower the number is, the brighter an object is. So that's why the magnitude, the lower numbers are higher. So, and it actually goes negative as well. So basically the scale was first established by eye views. So the brightest thing we can find, which was the dimmest thing, we set that at 0. Well, now we have satellites that can look farther and see more things. So now we even have negative magnitude things because it's on a logarithmic scale. the way it works is you can't put a negative in a log, but you can get a. I'm not good at logs myself. I need to get better at that since I'm getting more into astronomy. Suffice it to say that that's why you can look at the top of the diagram. You can see that some are going into like the negative a little bit, so you can actually have negative magnitude. I believe even Vega, our sort of benchmark star that we like base most of our magnitude measurements on, like that's like the measuring stick. Since we have more accurate measurements, I think even that is like slightly negative a little bit with our more increased measurements. So in the bottom, if I remember right, that's color. So basically the GB key and the GR key are sort of different filters. We're taking a difference between different filters to get the color, and which we know from previous videos that I did about the HR diagram. It's the color of the star is related to the spectral type. So it makes sense that the color at the bottom will be aligned with the spectral types at the top, which are related to color because we know the color of a star, like the blue of stars, will be hotter and the red of stars will be cooler. So that's that diagram there. Now the middle part is actually looking at some of the details of the actual campaigns. And let me actually check and make sure this thing is still working properly. So I don't have one like another one like the last time. Still saying upcoming. This thing's still not going. Put up here. Nope, it's saying live. Good. So the last time I need to check that. It's not the only time I did a stream where the thing didn't. I thought it was playing, but it wasn't. Maybe there's some kind of bug in my software, but everything's going now. And be sure to drop a line if you're watching. I see there's at least one there taking a look. Drop a line so I know you're there. Let me know if you have any questions or comments. And let me know of anything I can improve as well. If you see something I can improve on or a different piece of data you would like added into this poster. It's long been known that stellar rotation rates of stars with sun-like masses slow over time, such that the period of rotation is inversely proportional to the square root of its age. So basically, you take 1 over the square root of the age. That's basically how the rotation of a star slows as the star gets older. And one way that happens is, I'm sure there's more than one way. We know that the sun and different stars, all the stars have ejections of solar mass, solar winds, and coronal ejections and things like that. Well, when these things are ejected, they carry their momentum with them. It's like how we're in space and we had like a bowling ball, we're floating in space and we push that bowling ball away from us, or we would go back the opposite direction like Newton's third law. So when the sun or any other star is spinning and flings off some matter, or when it flings that away, the sun is slung in the opposite direction, which means that there's a little bit of momentum in the opposite direction slowing it down. So as the sun spins off and spits off parts of itself, the conservation of momentum says it has to slow down a little bit. So over time, now it's slightly different for bigger stars. Part of the reason why is because stars have differential rotation, means that different lines, or I guess what longitude lines of the star will rotate at different speeds. So the very center of the star will rotate faster, for instance, than the upper or end edges of the star. You're looking at the star as a rotating object with its poles. If you're closer to the pole on a star, you'll rotate slower. So if something has a lot of differential rotation, that can throw off the measurements and identify those as low confidence periods. But we're able to get a lot of very high confidence measurements with our increased precision, which we can see in the yellow part right there. Newer surveys increase the range and precision of data. For instance, Gaia EDR3 determined 100 million more rotators than Gaia EDR2. In addition to procuring increased parallax precision and improved photometric measurements. And that's just overall the use of these satellites, is my understanding. By these improvements, we updated the astrometric and photometric data in star catalogs. So basically, my understanding is either this group or whatever group had control of the satellite during that period of time, but if they're just using the data that was procured from those campaigns, they were able to focus the satellite on this particular area of the sky 3 times. Campaign 5, Campaign 16, Campaign 18, from 2015 to 2018. And interestingly enough, the last one you can see how it's a bit shorter than the other two. My understanding is that the satellite, the way it was placed, it wasn't placed in the most advantageous position, and it kept drifting out of position. So one problem that caused is the satellite had to, as it drifted, the image, the lens of the satellite moved, and the stars actually, moved in the visual area of the satellite. So they had to correct for that. And then when they had to keep firing the rockets to get the satellite back into position, that burned down its fuel, so it shortened its overall lifespan. So in the end, they had to shut down the satellite, essentially, and just use whatever fuel was left to send the data back. My understanding, that was the last time they can use that satellite. So my understanding what happened. So therefore, that last campaign 18 is a bit shorter than the other ones. And that did actually result in some less precise data because they wasn't able to get as much data over time, so it increased the amount of error. And so the 18 one, my understanding is it didn't yield is accurate data, but it still helped out. Now this is actually a view of Praesepe, the cluster of stars. And at this point, the satellite is basically focused on the center core of the cluster. You can see the declination on the left, the right ascension on the x-axis, and the location of the cluster in the sky. So, anybody, if you had a good enough telescope, you can point it in that direction and you'll see that cluster there, which, maybe I might try one day. I don't know if my telescope will be able to see it well enough. So it says K2 observations of this one is those of 2 campaigns, campaign 5 and 18. The pink dots represent stars with greater than 70% certainty as members of Praesepe. 868 stars were measured via both campaigns, with rotations determined by algorithms on photometric data from the stars. So the idea is that, there can be a star in between us and the grouping of stars, but that star may not necessarily be in the cluster, and there could be stars behind the cluster. So basically what they do is they look at the overall rotation rates of the different stars in the cluster, and if something is spinning very differently from the stars in the cluster, then it could be because it's not in the cluster. So they could use that amongst other things to determine whether stars are really in that cluster of stars or not. So that cluster formed from the same nebula. We talked about planetary nebula last week, if I recall. If the stars formed from that same nebula, then they would have similar angular momentums, thus they will rotate differently, but it won't be so different that, it's like, where's this star getting all this speed from, or why is it going so slow compared to everything else around it? Now this, read the caption, complete sample of rotators across all campaigns, single and binary stars. That's one of the things that I overlooked, as far as the fact that some stars, there's like 50% of the stars in this cluster are binary. So there's a lot of stars it seems. So binary is pretty common. So apparently they can be looking at a star, and I'll just talk about how they get the light curves momentarily. They'll be looking at a star, what they think is one star, but that star will be spitting out 2 distinct light curves. That's one of the ways they can determine that is actually a binary star. So, and again, that we have, and one thing I noticed is they used a smaller breadth of study. Like at the top one, it went all the way to 8 stars in size, but this one started at 3 stars. So basically the O stars, the biggest stars, then it goes to B, A, and it went to F. So I wonder why they cut out those stars to the left. But and we can see even at the bottom the color difference the previous one was in the negative it started from, but this one started at 0.5. So it was a smaller window within which they looked. Maybe those stars they determined they were not in the cluster, I'm not sure. Now this is actually a light curve. We can see actually how the light curves look. So basically what we're doing is ironically, and maybe not ironically, but I'll just say it's interesting that they pretty much use the same method I did when I calculated the rotation of the sun with the spots on the sun. We close enough to the sun where I could literally do a visual, inspection of the spot and see how fast it was going. Well, here we can actually look at enough detail of the star to get a see that that's a spot on it. But what we can do is look at the overall brightness of the star, and we know that a sunspot is going to dim the star. So we can look at the dimming of the star and how that dimness moves transversely across the star, and we could look at the period of rotation of that dimness, how that star is getting dimmer and brighter and dimmer and brighter. So basically, if you're in a period of high sunspots, that whole period will be dimmer. Fewer sunspots, that whole area will be brighter. And if you have consistent sunspots going around the sun, then you will have a transversing period of dimness. And we can look at that period of dimness and brightness and discern from that the period of rotation of the star. Just like what I did with the sun, looking at the sunspot go across the sun. So looking at the caption here, the light curve for star epoch 211891691, showing the change in flux of the star over the 74 days due to star spot transversal due to rotation. The figure to the right shows the algorithmically determined periodogram. So basically, when we look at this normalized flux, we can see how the flux is going up and down as to move across the sun, across the star. And if we were to put this in an algorithm that can tease out the periods of this rotation, this is an example of how pointed we could capture the rotation from the light curve. So they would establish that this star has a 1.59 day period of rotation by looking at the spots in the strong peak at that day shows that this is a very, very high confidence measurement of rotation. Right, so it's some interesting stuff. So basically what I'll probably do is try to look at the data when I figure out how to get my hands on the data from this survey and see if maybe I can find some way to analyze the data that's different, where I can discern something different about maybe this cluster in particular, or perhaps even better, rotating stars in general, maybe how they're distributed, how the velocity of rotation is distributed in a cluster or something like that. So we'll see how that works. And let me pull up the paper again as well. And I'll adjust the window size again. So this is the paper in question right here. And same title, 3K2 campaigns, year rotation periods for 1013 stars in Praesepe. Professor Rampali. Professor Cross is actually a professor or doctor at UT. So that could be another reason why Dr. Rampali was there as well, giving a talk. And as you can see, this is one of the images I took for the left image at the top on my poster. But there's a few more in there. I might even change it which one I have. This is what I was saying, how one of the campaigns had the camera sort of towards the right of the core, perhaps to get some of these stars on the sort of ridge or edge of the cluster. And another thing they did well in the appendix as well, they showed different measurements of stars from more or less confidence. So if you look at the top one on the right there, this would be more like one that had, let me increase the size of this window here. the one at the top on the right, this would be one that's more like a high confidence one. You can see how there's very little noise. It's pretty much only that peak. So the algorithm was able to very clearly pull out a period in the flux of the star over more than 70 days. But if we scroll down and look at the bottom one here, you can see how noisy it is on the left side. And the same type of graph to try to pull out a peak, you can see it's a whole lot busy, a whole lot noisier. So this would be one that has less of a confidence level as far as the accuracy, because the noise that's there. So it's pretty cool. So this graph on the left here would be from the actual data, the flux that's coming from the star, and seeing how that flux changes as a spot moves across the front of the star, dims it, and you can see how the dimness sort of has a slope to it because that spot is moving across the sun over time. So a different sort of side of it is dimmer than the other side, is my understanding. So as that's shown in how the light is distributed in the pixels of the receivers. So pretty interesting stuff. So at least interesting to me, at least. So I've been reading some more. I've already read one of the papers that was listed in this paper. Like the very first thing they mentioned is how Shumenich found that sun-like stars rotate more slowly as they age, with the 1/, square root of the age of the star. So I read that paper. It was on like one page, pretty short actually, and he just basically just laid out his finding. But apparently that made him famous because people didn't know that before that time. That was from 1972. I did read one of the earlier papers I went through was a survey of stellar rotation, and it did say that over the last few hundred years, not much more has been gleaned about stellar rotation. So that would explain why this paper apparently is more standard to use more current papers, but you know, not a lot has been found out since then. Well, I mean, you got to use the most recent paper that's there. Even these papers from 2013, 2010. So I'll be going through some of these and seeing if I can better understand what's going on, as well as see where I can find some kind of niche where I can find some interesting thing to focus on. So I'll be looking at that. Awesome. Sorry again for being doubly late the first time and then late the second time when I thought it was streaming, but it wasn't. But at least I was able to get a practice run. I think this one was a smoother talk on what I had here, but it also went faster because it wasn't updating stuff along the way. Like I fixed a few typos and things like that. But hopefully it was interesting to y'all. And what I'll do is I'll make sure, by the way, those who couldn't make it, who have to go to sleep, what have you, make sure you go ahead and comment on the actual video itself, and let me know what things I might be able to improve on the PowerPoint, anything I might change, anything you want to add. Maybe I'll change some of these images around. I already know a few things I might update, talk more about the conclusion that they had. And I'll see how I can make this poster better. Oh, I think I took the wrong one. Hold on here. Took the one that actually shows the poster. There we go. Yeah, so let me know your thoughts. Let me know if there's something I can change, and we'll look into more about how this stuff is basically constraining our understanding of how stars rotate. Eventually, we'll be able to, I think one of the things they want to do is better be able to determine the age of a star from its rotation. If you find a star with a certain mass and is rotating at a certain speed, since we know the decay rate of the rotation, if we know how fast the thing is rotating, as opposed constrained by looking at the general rotation of the entire star or what have you. I'm sure they won't be able to look at just the one star, since I'm sure not every cluster of stars starts with the same amount of rotation. But the idea is that we have an understanding and we can place that star's rotation in the distribution of rotation in the cluster. We should be able to get the age of the star just from that. So that's my understanding. So we'll see how it goes. And I think I might try to look into sort of what's the distribution of stellar rotation in the cluster. Maybe and they may have done it already. That's why I got to look at some of these other papers. See if maybe somebody already did plot out, how the rotation is distributed. Like you can see in this image right here, we can see this is the distribution of stars basically in proper motion. Like we could see how they're placed in the sky, and we can see, which stars are moving toward or away from us in space by looking at the spectra of the star, and maybe we can see and plot the rotation. Maybe understanding is the stars towards the center will probably be more massive, so they should be spinning more slowly, but maybe there's some specific distribution in that. Even I could even have to sort of also look at what I'll be able to understand and learn in the amount of time I have as well. So if you have any ideas, you can let me know. But awesome. Thank y'all for watching. Those who are watching, thank you for watching later. Those who will watch later, I'll be extra diligent about being here from our regular time next week at about 8 Central Time. And either I'll go in more in depth in some of the other things I learned from other papers that I'll be looking at, because I'll be looking at some more papers. I looked at this one, looked at the one that I mentioned earlier in the first page. I'll look at some others in this paper. Maybe I'll glean some more things to talk about this. Or if you have another topic you'd like me to talk about as well along the astronomy lines, let me know. There might be some more details about what else I can glean from rotation and see what the focus of my research will be when I actually jump into the data and try to discover something new in my research project. It's awesome. I'll see you all next time.